Hello, my name is Chris Barton, and today's presentation is on collisions in cryptography, the implications of the SHA-1 collision vulnerability found by Google Labs. This video is available on my personal website at http://marpaddroid.com/info-375-final. So what is the situation with the SHA-1 encryption algorithm? On February 23rd, Google announced that it created a collision of SHA-1 hashes on different documents. What this means is that they took two different documents and they were able to get them to have the same SHA-1 hash so that they look the same to a computer that would be checking via SHA-1. This is dangerous because a malicious actor could take two files, a file that someone would expect to be good, and a file they wanted to put malicious code in, and they'd be able to make it so the bad file looked like the good file. SHA-1 was thought to be vulnerable as early as 2005. The reproducible collision by Google is the first practical attack on the algorithm. Before this, other attacks were impractical because they'd take too much time or they were just theoretical. SHA-1 is still widely used by a large number of digital web services. Some of the services that still used SHA-1 were email for PGP signatures, HTTPS for secure connections to websites, Git for file validation, backup systems to replace changed files, and various other systems that need to be able to check a file's integrity or to see if it's been altered in any way. So what is hashing? Hashing is used by various systems and entities to cryptographically verify the integrity of a file. It is a complex mathematical equation that is used to analyze the file and assign a string of numbers and letters based off the binary content of that file. Hashes do not consider things like name, date, and other metadata during the computation of the hash, and instead look solely at the binary data contained inside the file. Generally, if you use one hashing function, you're going to get the same length string for each hash no matter how many different files you hash. So a 1 megabyte file will have the same length hash as a 10 megabyte file or a 23 megabyte file. And if you take a 1 megabyte file and you hash it, then change its name and hash it again, you'll get the same value hash on the output. What is a hashing collision? First, let's talk a little bit about how hashing is supposed to work. Due to the complexity of hashing algorithms, it's highly unlikely that two different files will have the same hash when put through a certain algorithm. Changing one bit in a file, then rehashing it, will cause what is known as the avalanche effect, where the whole hash changes substantially. As you can see in the diagram below, there are three values that are put through the same hashing function. Each one has a completely different hash sum, even though they're only off by 1 bit from each other. On the next slide, we're going to take a look at what would happen when there's a collision. A collision occurs when two files that are different at the binary level end up having the same hash sum after being passed through the same hashing function. This is a huge security risk because, like we said earlier, you could have a malicious file that looks like a safe file pass through any system that's designed to scan using this hashing algorithm. As you can see in the diagram below, we input 000 and we get out a hash sum. And then we put in 001 into that same hashing function and we get a different hash, highlighted in green because that's what we would expect. Then we're going to put in 010 into this hashing function. And lo and behold, we have a collision because it has the exact same hash as the very first 000 that we put through the hashing function. This is a very basic example of what a hashing collision might look like in the real world. Obviously, larger numbers would be involved, but the output would probably look about the same. So how did Google create this collision? Google leveraged part of the PDF file format where images were added into a PDF file. There's a header, and then there's the actual image data file. They were able to pad the image header file with pre-computed data in order to generate the sum that they wanted. This took over 9 quintillion computations, which, in easier to digest terms, would be 6,500 years of single CPU computations, or over 110 years of single GPU computations. Not something that someone's going to do at home right now. However, if you were a dedicated actor, like say a state or a corporation that was trying to, gain information on the competition and you're unethical, this attack would only cost you about $75,000 to pull off. Knowing how hashing works and how the collision is produced is all nice and dandy, but what are the potential implications? SHA-1 is commonly used for file validation on email attachments, so it could be used to get a malicious email attachment in through a spam filter. This could be used for a phishing attack, or something along those lines. SHA-1 is also used for email signatures on many corporate systems. If you've ever worked in an environment where you use Outlook, and you see that little ribbon next to an email that was sent, that means that that email was signed by whoever sent it. It's possible that someone could fake those signatures using this kind of an exploit. Backup control systems use SHA-1 to compare files when backing them up. It's possible that you could have a backed up file that someone else placed there that isn't the file you expect it to be, and it could run some malicious code. There's even been a case where someone has temporarily brought down a Subversion repository because they wanted to prove, coincidentally, that Subversion wasn't vulnerable to the SHA-1 exploit. This repository was the repository for WebKit, which is what most browsers like Chrome and Firefox, Safari all use to actually display web pages. It actually took a few hours to get the repository back up and running. I don't know if it was just hubris or if the person just didn't realize that they should set up a test repository to, test this kind of vulnerability. But the lesson here is you don't test on a live repository or on a live system anywhere. You always set up a test system in order to test whether or not a vulnerability, or actually any major changes, are going to work or affect your system in a negative way. So how is the IT industry responding? SHA-1 has actually been depreciated for a long time, so most new systems should already be set up using a different hashing algorithm. As of when Google released this white paper, Chrome had already been set to mark any website that still uses SHA-1 for its SSL certificates to be marked with an insecure warning similar to the one you get when you have an invalid certificate anyway. Firefox was planning on adding this functionality in at a later time. However, they immediately set their browser to do this as soon as the white paper was released. Git is currently looking at how to move away from SHA-1. However, the creator, Linus Torvalds, is not worried because of how he envisions Git being used. We'll go a little more in depth onto that in the next slide. So what's the problem with thinking like Linus Torvalds? Linus Torvalds, he's the guy who created the Linux kernel and Git. Perhaps he's a computing genius. However, he assumes that since he uses Git for C, and there isn't much blank space to be padded in C that couldn't be detected easily, that it's not a big issue that files uploaded to a Git repository could be padded to cause a collision. However, the problem is that not all repositories only host C code, and a lot of repositories even host binary blobs. These binary blobs could be padded, theoretically, to actually cause a collision with malicious software. There are repositories that do hold PDF files, and programs that maybe they have a user's manual embedded in them that's in a PDF format, so it might need to be able to call that PDF that could be stored in a Git repository in order to complete the compilation process for a build. The key here is not everybody is going to use the same product or the same environment in the same way, and to assume so is quite frankly foolish. So when a vulnerability like this is discovered, it needs to be fixed in all systems, even if the creator of the system doesn't think that it's necessary. So how do you protect yourself from this vulnerability? Well, like protecting yourself from anything, the first thing you have to do is look at the systems you have in use. You have to determine which ones use SHA-1 and identify a path to be able to change that or upgrade those systems so that they use a different hashing algorithm. You need to begin phasing out SHA-1 with other hashing algorithms like SHA-2. There are already guides available online for many web and email services to migrate to SHA-2 or to many other hashing algorithms. You also need to check your website certificates and verify that they're not signed using SHA-1. Usually, if you renew your certificates regularly, your certificate authority will have already upgraded you to a newer signature. Normally at this point in the presentation, I would ask if you had any questions. However, since this is an asynchronous learning environment, I'm going to say that I just hope that you learned something from this and that it was a beneficial experience. If you have any comments or questions, please feel free to email me or give me a call. I assume since you're on this page that you know how to contact me. If not, there are plenty of resources here that you can use to research what I've said even more in depth. Thank you. Have a great day.